Okay, I hope you've been enjoying the video introduction there. I'd like to welcome you all to the first of this semester's Library Lunchtime lectures. Our speaker today, Professor Levent Gürel, will give us the talk, as it says here, Computational Electromagnetics. What does it mean to break the world record in Bilkent? Before we start, I would like to ask all of you, as I shall do now, please could you switch your cell phones off, because we've had one or two cases where cell phones have gone off and interrupted the speakers. So for politeness to Professor Gürel, please switch them off. Professor Levent Gürel is professor in the Electrical and Electronics Engineering Department at Bilkent and also director of Bilkem. Is that how you pronounce it? I was it would be Bilsem or Bilgem in Turkish, but which stands for the Bilkent Computational Electromagnetics Research Center. In 1986, he received his bachelor's degree in Electrical Electronics Engineering from METU. He then moved across the Atlantic to the University of Illinois at Urbana and Champaign, where he took his MS and PhD degrees. In 1991, he moved to the Thomas J. Watson Research Center in New York and stayed there for 3 years before joining Bilkent in 1994, though I believe he's maintained links with the Urbana-Champaign colleagues and still works there occasionally. As you can see here and upstairs, he has published a large and vast variety of publications on this field, and the samples you can even, the articles there you're allowed to touch at the end of the lecture if you wish to look at them in more detail. Please feel free to do so. He's received numerous scholarly awards and honors, including awards from TUBA and TÜBİTAK, and most recently he became a fellow of the Institute for Electrical and Electronics Engineering, or IEEE, as it's more usually known, I think. Our subject today is computational electromagnetics, and Professor Gürel will give us a short introduction to this broad field before telling us more about his research and the research of his team at Bilkem. It says on their website they are interested in solving real-life electromagnetics problems using cutting-edge computing technologies, and I'll leave it to Levent to explain to us exactly what that entails. As the title of the lecture shows, his team are constantly breaking new world records in terms of solving equations. Most recently, I think in October last year, the equation they solved involved 205 million unknowns, which obviously is quite a lot. I can feel some electricity in the air and maybe some magnetism. You're attracted to our speaker. I won't make any more bad jokes. I shall let him take over and give his talk. Thank you very much. So I got this thing.
Thank you. Thank you, David, for this very nice introduction. What does it mean to break the world record in Bilkent? That's a loaded question. It may mean, like, how did that happen in Bilkent? Or it may mean, what did you have to do to be able to do that in Bilkent? In any case, it means something. We get sandwiches to start with, and to end with, we will also have a free T-shirt at the end of this talk, but not to everybody. We don't have so many T-shirts. We have one T-shirt here, so we will give that to one person after a drawing. You will have to answer a very simple question. David already told you the answer, but I will repeat that answer a few times during my talk, so that won't be a problem. But there will be too many correct answers, so we'll have a drawing. Okay, so on with the talk. I'll talk about computational electromagnetics, and then after a brief introduction, I'll talk about the large problems that we have been solving and some applications. Our mission is to be able to do electromagnetic modeling of any relevant problem in electromagnetics involving arbitrarily complicated geometries at any frequency. Now, this is by no means mission accomplished, but it's good to have a mission. It's good to have a direction to work towards. This means that we are not interested in solving simple problems. We need these the solution of these complicated problems if we want to solve real-life problems, because real-life problems are by no means simple. Here's a real-life problem. This is a picture from IBM. It shows a microcircuit with conductors that have dimensions in the orders of nanometers. That means the widths of these conductors here are in the order of maybe 50 nanometers, 100 nanometers, very small details. Now, this is basically a chip from a digital circuit. So on these conductors, we should have zeros and ones, the types of signals that we have in computers, the types of data that we have in computers. But you can also consider this conductor here as an antenna. As a signal of zeros and ones propagate on this conductor, it also radiates. It is just inevitable. It will radiate. And you can consider the next conductor as a receiving antenna. So it is possible that the zeros and ones propagating on this conductor, they may get radiated, and they may end up on this other conductor. That is the definition of a disaster. If that happens on a daily basis, your computers would not work, your cell phones would not work, nothing would work. So for that reason, people who are designing this kind of complicated circuits, they have to design this from the point of view of digital signals, ones and zeros, logic, but also they have to consider the electromagnetic side of it. Here's another real-life problem where we can model a nano-optical imaging system. By that, what I mean is like here is a laser light, which is a form of electromagnetic wave. And after some focusing devices, we focus that light onto a structure that we would like to image and see, basically. After scattering, electromagnetic scattering at this level, the scattered electromagnetic fields, I call them electromagnetic fields, but you can think of them as light, laser light. It goes back in this direction, and it is collected by some imager up here, so that we have an image of whatever structure that we would like to see. That structure that we would like to see can be this nano circuit that I just showed you, okay? And it turns out, if this is like a microscope using visible light, like lasers, the wavelength of the visible light is in the order of 500 nanometers. There's a range, but 500 nanometers is a nice round number. And there is a principle in physics that you cannot image or see a feature, a detail that is less than half a wavelength large. So in our case, in the case of visible light, the wavelength is in the order of 500 nanometers. So half of that is like 250 nanometers, which means that if these feature sizes are in the order of 50 nanometers or 100 nanometers, you cannot see them. You cannot see them. So in this respect, we have to give a lot of credit to people who are designing and fabricating these chips, because they're doing that without really seeing them. Now, that's an overstatement. They can see them, because there are other modalities of imaging. For example, they can use X-rays, atomic force microscopy, things like that, but not a microscope, not visible light. The reason I'm mentioning this as a real-life electromagnetics problem is the following. It is possible to take into consideration the electromagnetic scattering that is happening at this level, so that you can obtain images that have better resolution than half a wavelength. That means an improvement of the microscopes that we are using today. Here's another real-life problem that we are actually solving. This involves the electromagnetic scattering from red blood cells for the purpose of diagnosing blood cells that have diseases, that have peculiar shapes, so that we can diagnose blood-related diseases. A completely different real-life problem where we have several antennas mounted on an aircraft. This is the so-called AWACS problem. There are so many antennas that one needs to know ahead of time, hopefully, how these antennas interact with each other. When you install these antennas on an aircraft, what will be their performances? There are other examples of antennas mounted on platforms. Here's an antenna on a car. Here's an antenna on a cell phone. We all carry one. Here's an antenna or several antennas on a satellite. You would definitely want to know the performance of your satellite antenna before you shoot it up in the space. You wouldn't want to test it up there. You would want to do that down here. So electromagnetic modeling and simulations is a very good way of doing that. Radiation into living organisms. For example, everybody is using cell phones. And we all feel some guilt from time to time because we feel like we are grilling our brains. And it is true. I mean, there is, again, inevitable electromagnetic radiation. But the question is it harmful or not? This is what people are discussing. It's a good thing that people are not dying by huge numbers around us. So we think maybe it's not that harmful. But the real answer will come 30 years later. We need more statistics, okay? So you cannot, I mean, we know there are electromagnetic waves and fields in our brains when we use cell phones, but the answer is how intense is it? Is it really harmful? So there's no way to measure that. You cannot put little antennas, little probes in your brain, several of them, 100 of them, and measure. There's no way of doing that. But what we can do, we can actually compute the fields in our brain. So if you want to have a map of electromagnetic fields in your brain, you can, for example, choose 100 points in your brain and do the computation. That roughly translates to a problem with 100 unknowns, okay? But then, in your three-dimensional brain, you would have only 100 points of calculation. So you would have a map, a very coarse map of only 100 points. That would not be sufficient. In such a vital application, that would not be sufficient. You would want to have a much better resolution for a map of your brain, or for a map of electromagnetic fields in your brain. You would want to have millions of points in your three-dimensional brain. Don't just think of it, one-dimensional millions of points, but you put millions of points in the three-dimensional volume, so that you can obtain a very fine picture of the electromagnetic fields. But that means solving in the order of millions of unknowns, okay? And that's what today's talk is all about. Solving millions of unknowns with electromagnetic computations is not easy. I mentioned that we want to solve not just canonical problems, but problems with arbitrarily complicated geometries, geometries such as these. These are actual three-dimensional geometries modeled on our computers, and we have been able to obtain their electromagnetic solutions. Some examples I will be showing along the way. We take these geometries and we discretize them with little triangles. That's one way to model them. And then we want to solve any relevant problem, like radiation or scattering or coupling or propagation on these problems. Now, if you want to solve not just a simple problem, but any electromagnetic problem on these geometries, you need to solve the full Maxwell's equations, which look scary. They are coupled partial differential equations. Even more scary, we convert them to integral equations, and that's what we solve. These integral equations are defined on the surface of a structure, and we need to discretize these integral equations on the surface, again, by using little triangles. Now, if the object is large, if the wavelength is small, then you end up with literally millions of triangles on this object, and that again translates into a problem, basically a matrix problem, a matrix equation, but a very large matrix equation with millions of unknowns. This is a matrix here, this is the unknown vector, and assume that there are millions of unknowns. Now, what is a matrix equation? If you solve like 2 unknowns in 2 equations, that means a 2 by 2 matrix, okay? And this is what we have been doing, right? I mean, solving x and y in 2 equations. If you solve 3 unknowns in 3 equations, that means a 3 by 3 matrix. If you solve 1 million unknowns in 1 million equations, that means a million by million matrix, which is not so easy. But if you can do it, the result is sweet. You obtain let's say the current distribution or the fields radiated or scattered by this object or target in this electromagnetic problem. Here I'm showing the solution of the current distributions for different frequencies. At, let's say, 2 gigahertz, 5 gigahertz, and 10 gigahertz. What you see is that as the frequency goes higher, the details are finer and finer, which again translates into using more and more unknowns and solving larger and larger problems when the frequency is higher. So here I have a chart where I will be showing you a few of the solvers that we are using, fast solvers that we are using. Assume that this axis, just symbolically, is the axis of higher frequency or larger problems. Both of them mean the same thing, higher frequency or larger problems. Now, there are some techniques in electromagnetics, computational electromagnetics. My mom is not helping me, but mom means method of moments. Method of moments is a good technique to solve problems, but it will take you only up to so many unknowns or such a frequency. If you want to go higher, then you need to devise new methods, and that's exactly what we did. Fast multipole method will take us to larger problems. Multi-level fast multipole algorithm will take us to even larger problems. And then we start using the cutting-edge technology in parallel processing, and we parallelize these algorithms. We use parallel multi-level fast multipole algorithm to take us to even larger problems, more unknowns, higher frequencies. So I mentioned parallel computing. Basically, the idea is to connect a number of computers around a very special network and to use the power of all of these computers together. But in order to be able to do that, we need to parallelize our programs, which is not trivial, meaning that I have this complicated electromagnetic solvers. They are difficult enough to develop or implement them on a single processor, but now I have to implement them on several processors. And that is the trick or the task that we need to do. Now we have a number of high-performance computers here at Bilkent. One of them is a 64-core parallel cluster. There are 64 cores of processors in this machine, and a total of 256 gigabytes of RAM. Another machine with 136 cores, and this one has more than half a terabyte of RAM. This is the actual memory, not the disk capacity. So we are very happy to have large computers like these here at Bilkent. We actually constructed these computers with our expertise here at Bilkent, and we are maintaining them, running them. So these are all good things. We are very proud to have these machines. However, if you go to a website called top500.org, that website will give you a list of most powerful 500 computers in the world. Okay, and you can easily see, if you go down to the 500th computer, you can easily see that even our most powerful computer here at Bilkent is not in that list. Okay, so not being in that list actually means it is probably not in the first 1,000 or maybe not even in the first 10,000. So what that means is this kind of computers are not the world's most powerful computers. What we have here is actually quite modest. And I emphasize this because it's not just using very powerful computers that allow us to break world records or to solve the world's largest problems, but it's actually the solvers, the intelligent solvers that we develop and use on these computers. It is that aspect of our work that allows us solve the largest problems. Here's a technical slide. Here what I'm showing is with respect to the number of processes, and that goes from 16 to 32 to 64, what is the efficiency of parallelization for different parallelization algorithms? Now, what does that mean? What it means is this. Let's say we have 64 processes, and let's say you have a program, a computer program, which is solving a big problem. So it takes, let's say, 64 hours to solve the whole problem. 64 hours, that's several days. Okay? If you have 64 processes, can you solve the same problem in one hour? Instead of 64 hours, can you solve it in 1 hour? If you could, then you would have 100% efficiency. And that is very difficult to attain. The fact that you have 64 processors doesn't mean that you will be able to, or easily be able to use them with 100% efficiency. The difficulty comes from dividing different tasks in your program and assigning them to different processes. So, for example, these are three different parallelization schemes for the same problem. The top one belongs to us, and the other two belong to other people, other researchers in the literature. What we see is this. With 64 processes and with our parallelization scheme, we have been able to obtain almost 90% efficiency, which is really something. But with other schemes in the literature, we would be down as low as 60%. And that means that program which takes 64 hours on a single processor, we can solve that problem in a little more than 1 hour with 90% efficiency. We can solve it with a little more than 1 hour. But it would take, perhaps, if this was 50%, it would take other people 2 hours to solve that same problem. It's little things like these which are very important in parallelization, which allow us to solve large problems. So speaking of large problems, let me mention some of the problems that we solved at high frequencies. Remember, again, high frequency means large problems, or high frequencies require large problems. This is a 13 million unknown problem, which we solved some time ago. What kind of a problem is this? This is a simple sphere, a conducting sphere, and we are looking at an electromagnetic scattering problem. What does that mean? We have a sphere, and we send an electromagnetic wave to that sphere, and that electromagnetic wave, when it hits the sphere, it scatters in every direction, and that's what we are solving. Now, if that sphere was an airplane, you would appreciate this problem as a radar problem, because radar waves are coming and hitting the airplane and then getting scattered, some of the wave coming back. Instead of an aircraft, here we have a very simple sphere. And the reason we have a sphere here is the following. The red curve here is the analytical solution. The sphere is simple enough so that we can obtain an analytical solution. What is an analytical solution? It's a solution that does not require the use of computers. It's something that you can obtain with pencil and paper, almost. and maybe a good calculator. But it is an exact solution. Because you see, when I'm solving 13 million unknowns, that means 13 million by 13 million large, huge matrix problem, and it takes several hours of computing, and at the end I obtain 13 million numbers. Are these numbers correct? After so many hours of computer time, what if I just obtain junk? Who's to tell that these numbers are correct? And that is why we take a simple object like this, and we compare our computational results, the blue dots, to the red curve. The red curve is the exact solution. So even for the solution of such a large problem, we are right on the dot. All of our results agree very well with the exact solution. Now, I won't spend that much time with the rest of the slides because all we are doing is solving larger problems, 23 million, 33 million, but you can keep an eye on the accuracy of our results. They are still very accurate. The agreement is very well. 42 million unknowns, 53 million unknowns. The object is getting larger and larger in terms of wavelength. That means a higher frequency, larger numbers of unknowns. 69 million unknowns. 85 million unknowns. Now, if you want to do well on your quiz, this is the part that you should be following well. At this point, with 85 million unknowns, we have an 85 million by 85 million matrix, and if we could fit each element of the matrix in a square of 1 centimeter by 1 centimeter, and I challenge you that you cannot do that. 1 centimeter by 1 centimeter is a very tiny area, and you cannot write these complex numbers that I have. You know, each element of the matrix is a complex number with a real part and imaginary part with so many digits after the decimal point. So you cannot really fit it into a 1 centimeter by 1 centimeter square. But if you could, then the size of the matrix would be this large. The surface area is equal to the surface area of Turkey. At that point, some news media took notice of this world record, and they promoted it. This is important because this is a case study prepared by Intel, because we used their processors, Intel processors, to break the world record, to solve the world's largest problem. They decided to announce this worldwide, and they prepared this case study and they distributed it again worldwide. This is important because this is not something that we did to promote ourselves, but actually Intel did it for us. Okay, but then we kept on continuing to solve larger problems, 135, 167, and most recently 205 million unknowns. That is our most recent world record. Should I emphasize that? Yes. So if I draw that matrix again, as you can see, this time it's much larger. It used to be like this big with 85 million by 85 million, but 205 million matrix, it's this big. The surface area is actually 5 times of the surface area of Turkey. And this is a timeline of large problems that we have been solving. As you can see, 205 is here. It's in 2008. But we have been solving some very large problems, larger than 50 million, larger than, like 20 million. I mean, even this corresponds to something like 1 million unknowns, which we solved back in 2005. But since 2006, we have been solving the very largest problems in the whole world. And even today, there are only a handful of groups all over the world that can solve problems larger than, well, a few millions. I would put million as a mark. Okay. Now, what good is the world record? We are solving these very large problems, but what good is it? Actually, I already mentioned it. It allows us to solve larger problems. It allows us to solve real-life problems, higher frequencies. Here's an example. If we want to solve the radar problem of an aircraft, let's say with 100 million unknowns, we can solve only the fuselage, the body of the fuselage. But if you want to solve the wings and all of that, you need like 150 million unknowns. If you want to solve the whole thing, you might need 200 million unknowns. Just symbolically, what I'm trying to show here is that being able to solve larger problems will mean that you will be able to solve a complete problem. It is quite frustrating from time to time. We have a problem and we have a tool to solve that problem, and we run out of resources. We want to solve a large problem and we run out of computing resources. We cannot solve that problem. Thank you for nodding. Because some people actually experience this, and they show me some sympathy with this. This is a real life problem. The frustration is a real life problem. We want to solve an object like this at a high frequency, and we just don't have enough computing power to solve it. But with our algorithms and parallelization, we are able to solve the whole problem. Okay. Here are some applications that we can do with this kind of a computing power. Here's a radar problem where we have a transmitter sending a signal, and it is scattered by the object. I have a nicer video of this. The radar is sending a signal, and it gets scattered in many different directions, actually in all directions by the target. And what we are doing is we take this very complicated target, we take this wave, electromagnetic wave sent by the radar, and we compute the green waves that are scattered by the target. It turns out some of these green waves will also go back to the receiver. And that is actually how radars work. And we do the simulation of it. Here are like 3 different targets. An F-16 fighter, a stealth target called Flamme, which is designed by the French, and the NASA Almond. Now, everybody knows F-16. Stealth means a target that is almost invisible to radar. It does not send back radar signals when it is illuminated by a radar. We'll see if it is really like that. And the Almond is actually a benchmark object. It is a very well-known object, so that researchers in different countries, in different universities, they can solve the same object and compare their results. So that's what I mean by a benchmark. Here's the Flamme. Here are pictures of the Flamme. Again, this is created by the French in a research institution called ONERA. This is actually their measurement setup. There is a transmitter, and the receiver can go around the target. The target is here. Of course, this is a small scale of the target. And these are the results obtained by ONERA, measurement results obtained by ONERA, and these are the computational results obtained by us. As you can see, the results are agreeing very well. If you look very closely, you can see that they're not exactly the same, but that is fine because those are very low values of the electromagnetic waves. That was a comparison with the measurement results from France, but these are all our computational results. We can solve this problem at any angle for any orientation for different frequencies. Okay, now we solve this problem. I'll go quite fast on this. We solve this problem with 14 million unknowns, with almost 25 million unknowns, 33 million unknowns, and also a very large problem, 135 million unknowns. Now, here is how we can, again, show parallelization efficiency. We have 64 processors here, also here, 64 processors. And these different colors, I will not go into the detail of them, but these different colors show the time required by different computations on a single processor. Each column here is a processor. The white areas is the wasted time. The white areas are the areas or the times that we don't do anything with that processor. The reason we don't do anything with that is this. This processor, for example, here, whatever that is, 27th processor, it finished its tasks earlier, but this processor here, processor number 2, it finished late. So everybody else should wait for the processor who finished late. And that means wasted time for all the other processors. And this wasted time translates to less than 100% efficiency. Okay? And this is why we cannot have 100% efficiency. But the kind of efficiency that we have is actually great. You don't see a lot of white areas. And as I showed you before, we have something like up to 90% efficiency. Okay. So this is the largest problem that we have solved. Again, almost 205 million unknowns on a completely real-life problem, not just a sphere, but a stealth target. Is it really stealth? Well, that we can tell by comparison to an F-16. Here I have the scattering results of an F-16 and the French Flamme. What we are seeing here is when both of the targets are illuminated at, let's say, 30 degrees from the nose, we are looking at the scattering all around the target from, let's say, 0 degrees to 360 degrees. Okay? That's what we are looking at. The 30 degree, the scattering at 30 degrees is quite important because that's called backscattering. And what that means is we have a radar here and we illuminate the target at this direction. Now the target scatters in every direction. It sends back signals at every direction. But the direction that goes back to the radar is very important. Why is it important? Because more than 90% of all radars used on Earth today are monostatic radars, meaning the transmitter and the receiver are in the same location. So backscattering is very important. Even though the target sends the scattered signals in every direction, nobody can observe them. The receiver is only at one location, and that's the backscattering direction. Okay? So if we look at actually the observed signal by the radar, this is what we see on the radar screen. Okay? If we look at the observed signal, the green is for F-16 and the blue is for Flamme. We see that the signal scattered by Flamme at the backscattering direction is much lower than F-16, testifying to the fact that it is a stealth target, meaning that it doesn't send back electromagnetic waves to the receiver of the radar. It is possible that the radar who is sending the illuminating signal will not receive or will not be able to detect such a low signal coming back from the target. So stealth targets, they do scatter fields. If you look at other directions, they do scatter fields, but they are designed not to send back the electromagnetic waves so that monostatic radars will not be able to detect them. Okay. I also added in here the scattering by the NASA Almond. Now, NASA Almond is not a real aircraft or something. It's not a flying object. It's just a benchmark geometry. But we see that also the NASA Almond has quite low backscattering, meaning that at the backscattering direction it can be considered as a stealth target. Okay, we solved the NASA Almond also with very large unknowns, meaning that it's a very large object in terms of wavelength. The only problem we are having with the solution of such large problems is the following. We beat the purpose of benchmarking. We're supposed to we are supposed to validate our results by comparing our results to other people's results, but nobody is solving the benchmark target at these frequencies. So we have some difficulty there. Okay. The last application that I will show you is involving metamaterials. Metamaterials are artificial materials which are not found in the nature. They are man-made materials. We take some pattern and then we repeat that pattern periodically in 1 dimensions, 2 dimensions, and perhaps in 3 dimensions. And we obtain a crystal-like structure with this periodicity. And these objects or these materials, they display very peculiar electromagnetic properties. This peculiarity is actually to our advantage because we have been using the materials that are available to us by the nature for centuries and even millenniums. But now these are very new materials, and we can come up with very interesting applications. Here's one. We take these structures and we make a wall out of them. Okay, we make a wall. And these are all conductors, but as you can see, these are like ring-shaped conductors. To be exact, they're split rings. There are 2 rings, one inside the other one, and they're also split, and that's why they're called split ring resonators, or SRR for short. Now, we make a wall out of them, and the question is this a good shield? Is this a good electromagnetic shield? Now, if you ask me, I've been in this business for quite some time, what is a good shield? Well, definitely a piece of solid conductor is a good shield. Is this a good shield, if you ask me? Definitely not, because these conductors are not connected, and all of them are much smaller than the wavelength. So I expect that all the electromagnetic power will pass by this wall, and this is not a very good shield. Here's an experiment. We take this wall, we put it here. You see the cross-section of the wall. And here we put an antenna or a source, an electromagnetic source. And we want to see what happens behind the wall. Are the electromagnetic waves passing to this area? Now, orange and red and these hot colors mean that they do pass, okay? That means 0 dB. 0 dB means they all pass. Now, I have a different way of showing this. This is the frequency axis, and this shows the transmission. And 0 dB shows perfect transmission, almost perfect transmission, okay? So that's exactly what I expect. If I have a source here, this is not a good shield. All the electromagnetic waves will pass, and that's what we see here. Until we come to a frequency around 100 gigahertz, we see that transmission is dipping. It's going down. So around this frequency, this is a very good shield. Now, if I were to bet money on this, I would lose it, and I would bet it, because I certainly do not expect this. This is a so-called meta property. We do not expect a stop band in this frequency, but it happens. It happens because this metamaterial has these very peculiar properties. Again, if you ask me, what is a good shield? As I said, solid conductor is a good shield, but you don't have to have a solid conductor. If you also take wires, simple wires, but if you put them close enough, that would be a very good shield. This is very well known. Faraday cage is something like this. So if you put wires very close to them, and the closeness is measured by wavelength, so if the distance between them are much shorter than the wavelength, this is also a very good shield, and it's lighter and it's cheaper. So instead of using a solid conductor, you can use this. This is a very good shield. Now what I will do is I will combine these two geometries, so we have a composite metamaterial. Now, before I combine them, here I have a lousy shield, or that's what I thought, but around 100 gigahertz, it is a very good shield. Here I have a very good shield at any frequency, and I combine them, and let's see what happens. Let's just look at here before we look at this. When I combine the two, I expect that there won't be any transmission. Minus 15 to 20 dB is a very low transmission. 0 dB is here. This is good transmission. So this is exactly what I expect. I put those wires, which are very good shields. So no electromagnetic waves should pass. But look what happens around 100 gigahertz. I have very good transmission. Now this is definitely not something I expect, because the wires are always there. They have to be a good shield. The other rings, the split rings, they are supposed to be not so good shield, but it doesn't hurt to fill in the blanks with those extra conductors. So why would this structure actually pass anything? And especially at the frequency where the split rings alone act as a good shield. So I have two good shields together around this frequency, and they act as if they are not there. They pass all the electromagnetic power. So again, this is a meta property, and these are all computational results that we have obtained to demonstrate this. Okay, so I would like to finish by saying that all this work that we have been doing is actually the outcome of a multidisciplinary approach, where we have been combining physics, linear algebra, computer science, geometry, modeling, math, and computer engineering to be able to solve these very large problems. Thank you.
Thank you very much, Levent. If you have computer resource problems and so on, then obviously we won't worry too much next year in the library when we try and get a few more computers. We won't feel so badly off, I think.
Now, can we collect the quiz results?
Yes, that's the thing to do now.
Yeah.
If you wish to win the T-shirt, please pass your quizzes in. How are you going to...
Well, we'll just do a simple drawing.
Right.
We'll not worry too much about it. İçine atalım. Atalım. Any more? Any more quiz results? Okay. So I need somebody to do the drawing. Would you do the honors? Without looking at it, just pick one.
I can find mine.
All right, let's see. 205, that's the correct answer. Ezgi Çiçek. Güle güle kullan.
Congratulations.
Okay.
Well done. Okay, some people are already taking the chance to leave now,
Sure.
so we'll just finish off very quickly because you have a place to go. Let me again thank Levent for a very interesting talk. We don't, well, maybe I don't need that for this, but thank you. In exactly 4 weeks' time, on Thursday the 26th of March, we will have our next lecture by Dr. Marie-Henriette Gates from the Archaeology Department. I would like to take this chance also to thank, as usual, the library staff who worked very hard for these lectures, Ulku, Burcu, Tanses, and Tarek, and others. And also, I think Levent's assistants, Nilay and Shafak, have been helping very much with the posters and promotions, so thanks to them as well. Okay, hope to see you all again in 4 weeks' time. Thank you.